You're the last one?
Yeah, best slot ever.
Yeah. Actually, great crowd.
Okay.
So we're finishing with an academic presentation. Sort of?
No, more technical, I guess. Oh,
Yeah,
in between,
technical.
in between, in between.
You're from academia.
Yeah, from academia, yeah, but
Yeah.
I'm also doing a lot of reverse engineering, so.
And all this conference has been to bringing together people from the private sector, from academia, from law enforcement, and so on. So I'm happy that we finished with you.
Okay.
Thomas,
Okay.
you have the floor.
Okay, thank you. Hello, my name is Thomas Barbosch, and I'm from Fraunhofer FKIE. And I would like to thank everybody that's still here, even though it's the last slot. Today I'm going to talk about behavior-driven development in malware analysis. Might sound strange at first, so therefore that's actually the word cloud of the little paper I wrote for this presentation. And there are 3 words that actually should strike your eye. That's test, code, and malware. And you might be asking, well, there's one outlier, right? Maybe code and malware that works by testing. So, and that's what my talk is going to be about. So, how we could improve basically some parts of the malware analysis process by using basically something like test-driven or behavior-driven development. So, as a quick motivation, as you all know, really malware analysis continues to be tedious and very time-consuming. And some people might call it job security. You have to, if you really want to do profound analysis, you have to get your hands on it. And one of those tasks you're actually doing on a daily basis is the extraction of certain behavior from a malicious binary, let's say the network protocol or a DGA. And what you usually would do is you analyze the probably obfuscated binary code, and then you basically re-implement it in a higher language like C and Python in order to be able to execute this behavior. What happens is, what many people do, and I count myself in because I do it sometimes as well, is that you basically are a poor decompiler. You're basically just translating the code from assembly to Python, and the EAXs and EBXs are still floating around in the Python code. And also you don't actually ensure the functionality, so you don't know if it's really working for a lot of cases or just the strange corner case you picked, and yeah, the readability might be very poor. You don't have actually documentation of this code, how you can interact with this, so maybe other people you give it hand it out have to reverse this code as well. And yeah, the underlying semantics are sometimes not clear because you don't think about it, you're just decompiling it. So I propose maybe a solution to maybe improve this process here a little bit. So let's see how this might work. Before, I would like to talk about related work. Basically what we wanted to have would be something that we could automatically extract this malicious behavior. In theory, this actually works according to the academic papers that have been written. So we just pinpoint to behavior and extract it and have our self-contained binary. But in practice, there are so many open problems that have to be tackled that this stuff does not work in practice. And also, in many cases, it's not publicly available. So. Then what people also tried, and they kind of what I'm going to do is that they applied test-driven development to reverse engineering in order to improve it somehow, but they demanded that the source code and documentation is there, which is not always the case in case of malware. So then I thought about what I wanted to have of a proper solution in order to improve it. So what I want to have is that the analyst allows first to describe concisely and naturally what he's observing in the binary and what's the behavior and all its submodules actually doing in natural language. So by describing it, you're improving your understanding of it. Then during implementing it, I want it to work continuously. So I want to have my test that say, well, this submodule works and keeps on working while I'm working on another submodule maybe. And then the resulting code should be concise, documented, and readable. And finally, I would like to increase maybe the focus of an analyst by doing it. So my solution would be just to try something like a star-driven development process, in this case, behavior-driven development, and apply it to my web analysis. So before I'm going to talk about how I'm going to do it, I'm just giving a quick recap about star-driven development. And first, there was basically software testing, and what's in software testing, we're doing it since a couple of decades. What it actually does, it tests whether software does what it's supposed to do. And sounds trivial, but in the end, this shows also quality to the stakeholders. They maybe pay you for the software you're programming, and yeah. The problems here is if you're doing it infrequently, for example, if people did in a waterfall model, then you write a concept, you write the software, a couple of weeks you're doing the testing by another team. This does not work that good. Also, if you first write the code and then trying to test it, you won't have a very high code coverage of the tests. And yeah, if you don't doing it automatically, yeah, it's not that efficient. So people at the beginning of the millennium basically came up with test-driven development, and the idea here is that you write the test first, and then you implement actually what you're testing. So in test-driven development, we've got this this small circle here, and it contains three different steps. At first, you write actually the test of what you want to implement, and then you see the test fail. You execute it, of course, automatically, and then you implement as much code as you need in order to make this test pass. So this ensures that, for example, you've got ideally that you got 100% test coverage. In the last step, you're actually refactoring it, and refactoring is always a touchy subject because people, if you don't have tests and you have to refactor something on the other end of the software, you might break it on the other end side. So if you got tests and you get directly noticed that if you break something, well, then you're very confident to do it. Furthermore, those tests actually serve as a low-level documentation of your code because they show how to interact with the modules that you're writing. So programmers can read those tests and know how to use this code. So then people came up actually with behavior-driven development, which, in contrary to TDD, focuses more on a clear understanding of the software behavior instead of, let's say, on a function level and very low level. So they are a little bit high level, basically. And BDD emerged from TDD, and half a year ago, I read on their website, they're still discussing what's actually BDD. So there's nothing like in Scrum. They say if you don't do this, you don't do Scrum. They're more like, they're not that strict. They say, yeah, if you do this, this could be also BDD. The good thing, the important thing here to notice is that, well, the test cases you're basically writing are in natural language. So, and this allows you to first express your thoughts, like you're actually thinking. And even though you're expressing those stuff in natural language, you've got a strong theoretic foundation. Namely, you're using basically the Hall logic, which is used in order to prove the partial correctness of computer programs. Here on the bottom part of the slide, you can see the so-called Hall triple, which is basically PCQ, and it's there's a set of P's which are preconditions, and C is a command. And if this command is executed with this set of preconditions, then Q has to hold. Well, basically, this is then expressed in natural language like given, when, then. So a typical BDD test looks like this. Let's say you've got a coffee maker and you're implementing the scenario that you adding the sugar to the coffee. So given that the customer has pressed the sugar button, when the customer presses the cold button in order to make this or to brew this coffee, then actually the coffee should have sugar within it. So now I'm showing you how we could apply actually this to malware analysis. That's the overview how you would do it, how you could do it. So there are two phases. So we've got a preparation phase where you basically get your machines ready, your virtual machines ready, but also you're writing an initial end-to-end acceptance test of the behavior that you're re-implementing. And once this acceptance test passes, as we see later, then you know that you've 100% implemented this behavior. And once you've finished this preparation phase, you're going into the implementation phase, which is kind of inspired by this TDD cycle. It's the first you've got an observe step where you're basically looking at the binary and trying to understand what is happening. Then you're writing a test for the part that you're re-implementing. Then you're actually implementing what are you going to re-implement it, and then you're going to refactor it in order to make it nice and concisely. Now I'm going into detail of all the phases. First, I'm starting with the preparation phase. The very important thing here is you have to pinpoint basically the behavior at first in the binary. Otherwise, you won't be able to reverse it. So that's the first step. And what you're doing is that you're basically trying to find an entry point of this behavior. Just let's assume it's a DJA because we all by now we all love DJAs. So where let's say something is passed in, that's the S, the entry point, and then at some point the behavior or the algorithm that is associated with the behavior ends, and that's one or multiple exit points because there might be error conditions and so on and so forth. At those basically borders of the behavior, you would extract initial test data. So you're actually acquiring a set of input and output data and using this for an acceptance test. And this acceptance test basically guides you through the re-implementation process. Because at first, if you first execute it, you don't have any code, it will fail. But then if you re-implemented the behavior 100%, then this acceptance test will or should definitely pass. So as an example, again here, a DJA, how could one pinpoint a DJA? I don't have to say that much about DJAs. We saw a lot of them. So basically, there's a classification how you could classify them. So they're either deterministic or non-deterministic, or they are time-dependent or time-independent. And most of them are time-dependent. So what one could do is here basically doing a naive approach. A naive approach doing a forward analysis and just looking at the time sources. And the idea here is, well, if the DJA is really time dependent, then just break on all the time sources and follow the data to maybe the beginning of the behavior. This would be the forward approach. Backwards, well, if it's really a DJA, at some point those domain names that are generated get resolved by DNS, and well, then you could, for example, breakpoint on such APIs like getHostByName and follow it backwards to the code to the end of the behavior. In the paper, I explain another case, but yeah. Well, then we're coming now to the real re-implementation phase, and that's the first step, which is basically observing the behavior. And what we are doing is we're basically using a top-down approach, and first want to get a rough overview of the behavior of the algorithm, and then dive deeper into the sub-algorithms, sub-modules, and identify these individual features, as I call it here, and their interfaces. Very important is also that we first implement it on a high level, and then gather at those interfaces that we've basically identified this test data for other tests, for using it and for mocking it first. So this is what I'm going here to talk about it. Then when we know what part of the behavior we're going to implement, we're stating basically this test in a given then when form, and implement testing it from a high level. And basically one fundamental idea here is that we use a lot of mock objects and behavior that features that are very down into the behavior shouldn't be looked at first. This helps also to focus on one part at a time. So therefore, we just gather at the interfaces of those submodules test data and use mock objects. And those mock objects are typically used to mimic real objects. In software development, they're, for example, to replace mock objects that you cannot access due to timing constraints, like databases maybe, or non-existing objects. And here in our case, basically, we use those mock objects to represent parts of the code that we haven't understood 100%. Yeah. Then in the third step, that's an example actually how we would do it. So that's the behavior which has a main. That's the main behavior, and it consists of 3 submodules basically: initialization, another submodule called a main, and a deinitialization. And then this a main also has 2 submodules, a1 and a2. And what we are doing when we're implementing a main is basically we're mocking a1 and a2, and don't deal with this at first. So we're going from the top to the bottom. So in the third step, basically we're trying to make this this test for the submodule to pass, and write just enough code to do this. And again, we have to look at the binary. This is the valid system specification that we have to re-implement. And here we shouldn't care about optimization, because at this stage we should just get it first right and make the test pass, and then we can optimize it later. Namely in the fourth step, where we refactoring our code in order to make it more concisely and more readable. Refactoring basically is it's altering of the syntax of the code without altering the semantics. So there are so many refactorings out there. There's a very interesting book written by Fowler a couple of years ago where you can find a lot. In the case of reverse engineering, we might, for example, refactoring inline code that we've actually re-implemented, let's say a mem copy or something like that. We could break up complex expression or remove dead expressions, actually. At this point in time, we have a look at this initial end-to-end acceptance test that we wrote, and look, if it's passing, well, then this means that we've re-implemented the behavior from the beginning to the end, basically. If it does not pass, we have to go through this cycle one more time or several times. So let's talk a little bit about limitations and critics. So one limitation might be decrease in time efficiency. Yeah, that might be true. For example, if you think about TDD, people estimated that there might be a decrease in time efficiency of between 15 to 35%. But I think if you're doing it this way, the extra time may pay off to just several benefits. Like, for example, you're focusing on one part at a time. And the thing is that you, for example, having the code working constantly throughout the re-implementation process is very, very nice to have. So, for example, if you don't do it and you introduce a bug into your code, you could debug it maybe for half an hour, and this makes you also slower. Yeah, maybe this is more like a critic that, well, TDD, BDD, it's usually for normal software development. Why we shouldn't apply it to malware analysis? people say it's throwaway code, it's reusability might be not needed, and I would say that's not true. And we've got long-running projects that base on code of reverse engineers, and therefore it's for us it's important to have this this code. So in order to show you how you could do this in practice, I want to do a case study on NiMame. It's a malware dropper. And yeah, unfortunately, I picked the DGA of NiMame. Yeah, so anyway, NiMame, it's a malware dropper mainly, but also it's using parts, I think, of the pony loader code in order to steal credentials. It has SOX proxies. What's very interesting about the family is that it's very heavily obfuscated, so you will see that in a minute. And I think, especially in those cases, what I'm proposing here helps you a lot in order to get this stuff done more efficiently. There's a little bit work on decompiling of an older, not decompiling, of deobfuscating. This code of NiMame by Daniel Plomon called IDA Patchwork. It's an IDA Pro plugin. But those guys keep on obfuscating and then obfuscation. So yeah, it's unfortunately those are very good. So here you can see a sample, unpacked trial example I've analyzed this summer. And what you can see, if you can see it, is that it's unpacked. The functions look quite regular. There are no strange constants. Actually, those constants that are there are annotated by IDA Pro, so that's quite useful. The imports are resolved. They seem also reasonable. So you first set some socket options, and then you're doing some error operation on the network API, so that seems reasonable. The control flow also seems reasonable. So if you got experience in reverse engineering, you could read this more or less like a book. In contrary, if you look at an unpacked malware sample, you see that it's full of irregular functions. There is no clear function end, no clear function entries. Also, there are strange constants, and actually those strange constants are, for example, used in order to dynamically compute the control flow. Furthermore, this also confuses the disassembler, so IDA Pro gives you very poor results, and it's basically very, very hard to statically analyze it statically, but also it's very hard to analyze it dynamically because all those control flow changes and those dynamic control flow computations also mess a little bit with your breakpoints, and that's not that much fun. What I used for tools for basically re-implementing the DGA is that I used standard tools, Immunity Debugger, IDA Pro, used Mandiant APT DNS in order to fake DNS responses. We implemented the behavior in Python and used as a BDD library behave. Later on, I'm going to push the source code to Bitbucket, so you can have a look. And I think that's always better than talking about source code in slides. So you should definitely have a look and see how one could do this. So what I did was that I did some first observations. I did some basic black boxing, and what I saw, the domains that were resolved were basically looked like hard-coded domains. First, there was a connectivity check to Google, and then something else which looked rather hard-coded. Then, when those domains failed, when it couldn't contact those domains, basically it started to generate random domains, as you can see there. And I checked it basically quickly in 2 different VMs, saw that the results are the same, and basically then it's deterministic, I supposed. And basically then I changed the time and saw, yeah, that's time dependent because on different dates the domains are different. So what I did basically, yeah, I thought we could break on get system time, and bingo, it worked. So I knew that this was was important API for the DJA, and we had actually the import which was the time, more specifically a certain struct that is returned by get system time, which was then later used as a seed. And it outputted basically 30 domain names. So then, basically, still in the preparation phase, we already knew very important parameters. So we knew the start and the exit point of this algorithm, so the interfaces. So then we basically let the binary run. I breaked at the beginning, I breaked at the end, let it run, and gathered basically the data at both ends, and wrote an initial acceptance test, which guided me through the implementation and showed me when I've basically finished the behavior re-implementation. So this was basically the first scenario I wrote, the first this initial acceptance test. And this is describing the whole behavior. So the scenario was that NIMEMDJ computes domains on a specific date. Given this date, blah, 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 that when the DJA computes the domains for these dates, then the domains should be blah, 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 and there were 30 domains. What happens is if you execute it without having written code, it fails, and yeah, well, I had to re-implement it. So what then I entered the cycle first. I was in this observing phase, and I stepped through the code and noticed that there are several algorithms involved. Like there was an initialization where the seeds, the time was used, and this was there was some computation with the time and some hard-coded seeds. And then it entered in a main logic. And in this main logic, the domains were generated, and this main logic communicated with another module, which was a pseudo-random number generator, which later then turned out to be source shift. And what I did basically, I focused on one component at a time, and first reversed the main logic and mocked the rest. So that's only part of the main logic. What I did is try to follow through it. I did it in the debugger. I found it to be easier than doing it statically due to the heavy obfuscations, and basically came up with this code. And then parts of this is only the main module, and all the stuff that is that is called. From there, it's still not implemented. So then I thought, well, it's now time to focus on another part, going one step deeper, and looking at how to basically compute the TLD of a domain. So basically, I mocked everything, the rest, and then I came up with the scenario for re-implementing this part that actually computes the TLDs. So I've given a scenario that the NIMEMDJ chooses the correct TLD from a set that I saw there, and given some seeds, when the TLD should be computed, then basically the TLD should be RU. And then I consulted the binary, we looked how it is done, we implemented it, did the refactoring, moved on to the next part. Then I already talked about this, the seeds and the pseudo-random number generator, which was another module I first just mocked. So I had seeds that going in, seeds that coming out, and furthermore some random number that was generated by it. That I used for my mocks. Now it was time to really dive into this pseudo-random number generator. At this moment, I didn't know anything about source shift. So I reversed it, and as you can see here, this takes 5 integers. 4 of them are seeds and one modulo, and outputs an integer in the range of them from 0 to modulo -1. So one has to be careful here because the seeds, the execution of this pseudo-random number generator had basically side effects on the seeds. So then I came again first with a test, what I wanted to test, and I dived into the binary, we implemented it, we factored it, we moved all the EAX and gave it actually, I think by this my colleague Daniel could quite easily see that it's XOR shift when he prepared his slide for his presentation, because actually they use in a Wikipedia entry, they use also ABC, so it resembled then quite nicely what the original implementation looks like. So the results basically were that this whole feature at the end passed after a couple of tests that I wrote for further submodules, and that the code basically was readable. It was split in several classes, and yeah, that's the outcome. Basically, confusion and future work now. It's today I showed you how you could improve the malware analysis process when you re-implement behaviors. I told you why you want considering this approach. And I showed you a case study on IMAME, and the source code and all the tests and slides in the paper will be also on Bitbucket, so you can check it later out. Future work would be to automate a lot of this stuff, what I'm done here manually. For example, tools for just gathering the test data at the interfaces, just giving it to, maybe writing a tool and giving it 2 points in the code, and then executing it and gathering the input and outputs, and using it also for automatic test case generation maybe, in order to further improve this. So thank you very much, and I'm open to questions.
Questions?
Very good conference, academic presentation. Because you want to use test techniques from software engineering to malware analysis. It's a very good idea, but you can't. You are only on one in specific case, because you can apply whole logic only to one single model, deterministic and sequential. It is not the case. You can't apply these techniques to multi-model, asynchronous, parallel. Okay. In the next step, you must use formal methods that have semantic of non-deterministic behavior, asynchronous, and with more complicated theoretical.
Sounds definitely interesting. I guess there is no framework for this yet. So BDD is relying on it, but yeah, we can talk about this later. Sounds very interesting. Thanks.
Another question? Really? The last question of the day? Okay, thank you.
Okay. Thank you.